this really quickly. Okay, yeah, let's go back. Yeah, sorry for the late start. And today we are going to talk about, I think it is the most famous quantum algorithm, that's Shor's factoring algorithm. And we're already seeing the quantum part of the algorithm. And so today is actually mostly we are going to talk about classical number theory. But yeah, but let's go over a bit of a review of what we did for the factoring. Okay, so to do factoring, we actually start with another number theoretical problem. Let's see. So now we'll talk in terms of how we're going to do the factoring. Okay, and so this big N will be a number we are going to want to factor, and and to factor this bigger number, we'll find basically just a random x such that x is coprime to n. If x is not coprime to n, then congratulations, you already find the factor of n. Okay, and so you find a random x, and then you try to find something about x and n. That is, you want to find the order of x with respect to n. And that's defined as the smallest possible number, smallest possible integer r, such that x to the r power equal to 1 mod n. And here we have some example of being an order. So if your n is 7, obviously you cannot factor this because it's a prime, but anyway we can still find its order. Okay, so n equal to 7 and x equal to 3, then you keep multiplying these 3. And you see that you multiply x by itself 6 times, and then you go back to this, it goes to this mod equal to 1 mod 7. Okay, and so r equal to 6 for this pair of x and n. Okay, and this is a part of number theoretical problem that can be done really fast with quantum computer, but not so fast in a classical computer. At least we don't know. So classical computer, we need about 2 to the L number bit of n to do this problem, and what you do is you multiply x mod n. Okay, so you do phase estimation on this, and yeah, and you see that the phase we get is related to the r we get, because the eigenvectors of this weird unitary is our superposition of all the possible power of x mod n. Okay, and yeah, and you can use some phases on it. So there are actually different eigenvectors. You can construct it from those different powers of x under mod n. And yeah, and there are those. So us with s, u sub s with s from 0 to r minus 1, and here are some equation for them. And yeah, and you write it out. It's just really normalized of those kind of things. So u0 will be just equal superposition of all the power of x, and u1 will be the superposition of power of x times omega to the power of x, and then u2 will be omega squared to the power of x here. And yeah, and so you have any one of those eigenstates, you can do phase estimation on it, and you will find s over r. Okay, then s over r is really, then you see that you know s over r, then you know a lot about r. But you cannot control those eigenstates, and so we do something really funny. We use this Fourier transform relationship to see that if we add all of those us together, then you actually get this one state. So 1 is the equal superposition of all the possible us. Okay, so if you do phase estimation on 1, you are basically doing phase estimation on a random s. Okay, and so you just do phase estimation with the eigenvector, you use 1 here, then you will get the s over r with the random s. Okay, and yeah, so that's basically how you do order finding. You do phase estimation with the eigenvector being 1, and you get random s over r, and you can infer r from here with a little bit of calculation. Okay, and yeah, that's the order finding algorithm. We have a sketch here. Here is the sketch of we writing our face estimation with with a bit more detail. Sorry, this is we're writing down the order finding algorithm with detail. So we write out details of face estimation, and then we also see that when when R is not power of 2, then you will get some accuracy issue. So when R is not power of 2, then it's S over R. Sorry, this 2 to the T S over R might not be an integer. So you will get some accuracy issue, and that's why we need to take our T to be large enough to cover our accuracy. Okay. And also we say that we get a random S over R. So this is something we'll cover in more detail today. So we'll get a random S over R, but that don't tell you what's R. You just get S over R as a number. Okay. And sorry, typo. And so you get a random over S over R, and how you get R is you get a different S0 over R0, S1 over R1, and several of them, and calculate the least common multiplier. Okay, and we'll see that in more detail. Okay, and any question? If not, then we talk about there are 3 tricky points about this order finding. Okay, so first one is we don't want to do face estimation efficiently, and face estimation efficiently. We talk about this when we do face estimation. We say we need to do this this unitary to some exponential power very fast. So we need to do ux to 2 to the j very efficiently, and this can be just done by repeated squaring. Okay, so if you want to calculate some basically classical calculation, you want to calculate x to the 2 to the j, then you just keep squaring things. So you say x squared, you multiply x together to get x squared, then you multiply 2x squared together to get x4, and you can multiply 2x4 together to get x8, etc. And you see that in this way, you want to get x to the 2j, x to the 2 to the j, you only need to do j operation. So for example, you want to get x to the 16, then you only need to do 4 multiplication. Okay, and this is exponential improvement compared to just multiply x 1 by 1. So if you want to get x16 by just multiplying a whole bunch of x together, then that's direct multiplication, we need 15 multiplications. Okay, so that's repeated squaring that let us do face estimation efficiently. And the next part is that the error part we talk about, that's when 2 to the t or s over r is not an integer. In other words, and 2 to the t is not divisible by r. And in that case, your face estimation will not tell you exact number. Okay, so here you will not get exact number, but we have enough the accuracy to deal with that. And but even we have a lot of accuracy in this number, we still need to write it back to a fraction, because because it is a fractional number, and we are just going to get a good approximation to a fractional number, but we want to write it back to a fractional number, and that's how we use continued fraction. And the next part is what we talk about. That's when S and R might have some cofactors. So say if your R equal to 6, S over equal to 2, and so your S over R is 2 over 6, and you will learn this number as 1 over 3. So you don't really know, so when you get S over R equal to 1 over 3, you don't know whether R is actually equal to 3 or R actually equal to 6 or 9 or something else, because X and R has cofactor. And to deal with this, you find multiple Si over Ri and find the least common multipliers between different Ri's. So this is 最小公倍数. Okay, and I guess we can stop here for a few seconds. So people question about what we are going to do with this. These are the details of order finding. If not, then let's yeah, let's continue with the details of order finding. And as we said, repeated squaring just solve the problem of getting this x to the 2 to the j very efficiently. Okay, and we do a classical calculation here, but because we know the oracle is basically classical oracle is equal superposition of computation on basis computation on computational basis states. So you can always turn a classical computation to quantum circuit with about same number of operations. Okay. And then we go to the order finding. I think we also covered this a little bit, but let's go this slower. Okay. And so the continual fraction says that so you get some number that's approximating to your S over R, and then you ask how to find S and R, and we use this continual fraction. So we have an example to show that how continual fraction roughly how it works. So we have a number phi equal to 0.25001 that looks really like 1 over 4. And we use continual fraction to say it's 1 over 4 by saying that you keep flip things around here. So you say it's 25001 over 100000. And so you flip this around this fraction, so it's 1 over this 100,000 and over 25001. Okay, and then you divide this with quotient and remainder. Okay, so you divide this thing and you see the 3 plus the remainder being 24997 over. I think 24997 over 25001. Okay, and you flip this around once again, it's 1 over 25001, 24997, and then it's other thing. Okay, then you do this division again, then it's 1 plus, this is just 4 over 24997. Okay, and then we say that when we see something very small, we can just throw away this part, we say it's 0, and then you add it back, then you see it's 1 over 4. Okay. And so the continual fraction of some number is just you keep doing this flipping around. You have a over b, then you say it's 1 over b over a, and then b is bigger than a, you can do division, and you keep having more layer than layer. Okay. And then we just claim that if you cut off this continual fraction at some pseudo points, some super number of level, then you will get approximation to, then you will get your S over R correctly. Okay, and here is a very vague theorem, which didn't, it says that if your psi has your phi has enough accuracy to your S over R. So the difference is less than this 1 over 2r squared, then you can find your S over R in continual fraction. And but we just say cut off some level, so here we don't have a detailed proof. I guess we don't even have a detailed theorem, but you can look up Nielsen and Tron to see if you want to see more details. Okay, and so if we cut off the continual fraction and the order error level, meaning that you only need to do order error operation here, and we say we can find S over R, and then the number of accuracy we need is we need the error on psi to be less than 1 over 2 to the R squared, and we see that we have set up our accuracy enough to actually have error less than this, because we say we have 2L plus 1 bits of accuracy, and that translates to the error will be less than 2 to the minus 2L plus 1, and just because 2 to L equal to n, and n is bigger than R, so this is 2 to the minus 1 is 1 over 2, and this 2 to the minus 2L is less than n squared, which is less than R squared. Less than n squared, so 1 over n squared is less than 1 over R squared. Okay, And so we say we have enough accuracy to apply this theorem. And in homework, we will prove this partially. Okay, so we actually don't do the analysis on continual fraction, but we will prove that if the error here is small enough, then there is a unique S over R to be found. Okay, so yeah, so if S over R minus psi is small enough, then there is a unique S over R that you will find as a close fraction to your psi with R not too large. Okay. Anyone okay with this? Yeah. And okay. Yeah, and if we are okay with this, then let's finally go to the next part. And the next part about the details of order finding is we need to deal with different S over R when S and R might have cofactors. So we say we get S1 over R1, which is actually equal to S1 prime over R, and S2 over R2, which is equal to S2 prime over R. Okay, so here we have a bit of funny notation. So we say the random S, which we actually get we actually call the random S prime. Okay. So there's S1 prime, S2 prime, etc. They are the uniformly random number from 0 to R minus 1. Okay, so we draw those random S1 prime, S2 prime, etc. And then we say when we divide all their cofactors, we get S1 over R1 or S2 over R2, etc. Okay. And then we say that if we just do two of those, and so we get some S1 over R1, S2 over R2, and we find the least common multiplier between R1 and R2, and you will have a pretty good probability. So you have a wonderful probability to be equal to R. Okay. And so we can just keep doing this order like maybe 40 times, then we'll have a very good probability to get the R we want. Okay. And and the proof is that so we start doing more things. Okay, so obviously, if you want to have this to be so the least common multiplier of them to be not equal to R, then none of them can be R. If any one of them equal to R, then obviously the least common multiplier will be R. Okay, and so if you want to be not R, then basically R1 cannot be equal to R and R2 cannot be equal to R. And that means this S1 prime and R has some common factor, and S2 prime and R has some common factor. So we will take out some factor to get this S1 R1 and S2 R2. Okay? And so let's say the common factor there must the common factor must compose of some primes, and so basically there should be some prime number such that the prime number divides is part of the prime factor between S1 prime and R, and also between S2 prime and R. Okay, and that's because so here we are going a little faster. So how should I say? Yeah. So here the idea is that I guess here from we go from R to R1 and let lose some factor, and R to R2 must lose some factor. Okay, so think about there is something. So R divided by so R divided by R1 must be some integer, and R divided by R2 must be some integer, and so this thing is composed of some primes, and this thing is composed of some primes, P1, P2, and this is maybe Q1, Q2, and we think about R1 lose some prime to become R get divided by some prime to become R1, and R get divided by some prime to become R2. And if those two sets doesn't intersect, then the least common multiplier of R1 and R2 will just go back to R. Okay, And so for the least common multiplier of len to be not equal to r, these two ratios must share some common prime. Okay, and then it's a common prime. We just call it q. Okay, and so q will divide. Q will be a vector in S1 prime, be a vector in S2 prime, and also it will be a vector in R. Okay? And yeah, so I guess it is the most technical statement here. Any questions so far? So we're saying we have this R being a number we're trying to find and draw random S1 prime, S2 prime, and we see how how this S1 prime over R and S2 prime over R can be simplified to the two numbers co-prime to each other. Okay, so I guess I should say we are writing down S1 R1, S2 R2 as the simplest form. So we have the greatest common divisor of S1 R1 equal to 1 equal to GCD S2 R2. This is the notation we are using. Okay. Oh. What? Why do I? Anyway. I guess right. Okay. So GCD S1 R1 equal to GCD S2 R2 equal to 1. Okay. And so 这是最大公因数。So this S1 R1 S2 R2 they are co-prime to each other, and then we want to ask whether this R1 R2 in what case we'll have R1 R2 not have their least common multiplier equal to R, and that's when they both lose some prime factor. Okay, and if they both lose some prime factor Q, then the least common multiplier of R1 R2 will be will be at most R divided by Q, because Q divided by everything, and so we take the least common multiplier here, then this will be at most R divided by Q. Okay, and so this is really the bad case that happened, and we want to say this thing happened with not too much probability. Okay. And what we are going to do next is we are just going to look through all prime numbers. Okay. And so we want to see what's the probability that some prime number divides S1 prime and divides S2 prime, and also divides S2 prime. Okay? And but we know, so we are just seeing, we draw random S1 prime, random S2 prime, and see whether Q divides them. Okay? And yeah. And then we see this, and but we know S1 prime and S2 prime, they are both drawn uniformly random from 0 to R-1, and so S1 prime, S2 prime drawn uniformly random, I guess from 0 to R-1, and S2 prime drawn uniformly random from 0 to R-1, and here is also R-1. And because they are drawn independently, so the probability of both of those things happen is just the probability they draw independently. Okay, and so that's the probability that Q is a vector of S1 prime, and also Q is a vector of S2 prime. Okay. And here, I guess we also say we also treat a little bit. So we say it's drawn not from 0, because when you get 0, then really there's nothing. Okay, you can get nothing about R. You just get 0 here. Okay, so 0 is kind of a singular case. So we say that's drawn from 1. Okay, so S1 prime from 1 to R-1, and S2 prime from 1 to R-1. And then because it's uniformly random, then you can easily see that each of the probability will be less than 1 over Q, because for something you see that every single q can have q possible numbers, and only when it's zero mod q, this thing will be divisible by q. Okay, and so you draw a random number, it's really 1 over q probability that the number is divisible by q. And so each one of them is less than 1 over q, and multiplying together is less than 1 over q squared. Okay, and then we are basically just down here. Okay, so this is for 1 over the q. For 1 over the prime q, and then the total probability that they have no count vector is 1 minus all the possibility that you can get wrong by some q, and so you just have 1 minus sum over O prime, such that q being O prime, so O possible prime, such that the q is a factor of S1 prime, and the q is a factor of S2 prime. And then we already proved that this probability is less than 1 over q squared, so that's less than summation q being all the primes 1 over q squared. And then you basically can sum over this 1 over q squared, so you can instead of summing all prime, you can just sum in q from all integer from 0 to infinity, 2 to infinity, and then you can bound this thing with 1 over 4. And the detail here, and but I guess the detail here, so this inequality here can be done in homework. Okay, so that's also proved in homework, but it's not too hard. Okay, because you just know it's 1 over q squared tail, and you know integration of 1 over q squared converge, and so the summation also converge. And so that's complete proof that says that if you just draw 2 of the S, so you draw S1 and S2, then have its corresponding R1 and R2, then with at least 1 over 4 probability, you get a correct R, and so you only need to get a constant number of times to get a very, very good probability, to get the arbitrary constant probability of getting the correct R. Okay, and if okay, then let's see order finding algorithm with some example. So here is the example of n equal to 15 and x equal to 7, and it's a nice example because I think R equal to 4 here. Okay, and anyway, so let's see the order finding algorithm with numbers. So we start with first T register being 0 state, and let's L register being 1, and then next step, so the next 3 steps we do phase estimation. So first is first step of phase estimation, we create equal superposition on the first register, and that gives us this 1 over square root 2 to the t, and the summation j from 0 to 2 to the t minus 1 j, and the second register 1. And we apply this control ux on the second register, control on first register, and so second register becomes s to the j mod, and so that's first register 0, then it's 1, and the first register 1, then it's 7, and then you multiply 7 together, again mod 15, so this is 49 mod 15 equal to 4. Okay. So this is 7 times 7 equal to 49, mod 7 equal to 4, and then you have 49 mod 15 equal to 4, then you have 4 times 7 equal to 28, mod 15 equal to 13, and let's say you have 13 times 7 equal to 91, and mod 15 equal to 1, etc. Okay, and so here you see R equal to 4, so there are only 4 possible values in the second register, so it's 1, 7, 4, 13, and you should continue with 1, 7, 4, 13, etc. Okay, and then first register going from 0 to 2 to the 11 minus 1, so that's about 2000 numbers here. And then you apply inverse QFT to the first register, and you will get these numbers. Okay. Mm, sorry, I think 2t I think here we are having a bit of yeah, I think here might have some typo here. But anyway, so the next day we'll apply inverse security to the first register, and we'll get something. And but I think we should get actually those things. Okay, we should actually get only 4 things. Okay, so we should get 0. 0 plus 512 plus 1024 plus 1536. Actually, we only have those 4 possibilities on the first register, and when we measure, then we will get 4 of them with equal probability. Yeah. Here, okay, so this is a little a bit weird here. Okay. So this thing is, this thing is something we'll talk about later. Okay, and excuse me. And but anyway, so yeah, so this is thing we should get. So apply inverse QFT to the first register, we should get about equal superposition of those things. Okay, so this register here, it should be those 4 possibilities. So let's treat a little bit, and so we know r equal to 4, and so 2 to the t, so we should have 2 to the t divided by 4, so divided by r equal to 2 to the 11 divided by 4. This should be 2 to the 9 equal to 512. Okay. And so for the first register should be 512 times 0, 1, 2, 3. Okay. So first register should be this thing, and the second register should be times U0 times and so this thing times U1, and this thing times U2, and this thing times U. And yeah, so apply inverse QFT, you should get those 4 states with equal superposition, and so with 1 over square root 2. So with amplitude 1 over 2 on each other. Okay. So the actual state we get should be this whole thing times 1 over 2. Okay, on this step. Okay. And yeah, and then you measure the first register, you should get 1 of the 4 number here. So 0, 5, 1, 2, 1, 1, 2, 1, 0, 2, 4, and 1, 5, 3, 6. And then next step we want to get our R, and then we assume that we get 2 random one of them. Okay. And say we get 1024 and 1536, and although we have a perfect accuracy here, so we don't quite need continuous friction, but still try to do this. Okay, so we have 1024 divided by 2048, and then you see that easy see that reduce 1 over 2, and then 1536 over 2048, then you can try to do continuous friction, and you see it just ends very quickly itself. So you don't need to chart off, and you see that it has end somewhere, and it's 3 over 4. Okay, and then you have your R1 equal to 2 here, and R2 equal to 4 here, and you see that the least common multiplier equal to 4, and you see R equal to 4. Okay, and yeah, sorry for confusion. And so this thing will get, hopefully today we'll see something similar to it. At the end of the slide, we'll see why we're writing down this state. Okay, yeah. Okay, and so that's Shor's factoring algorithm. Any questions so far? So sorry, this is not factoring algorithm. This is order finding algorithm. Okay. If I'm okay with this, then I guess we can. Yeah, let's do a really quick sketch of factoring algorithm, and let's go to a break. Okay, and yeah, so with the order finding algorithm in hand, now we can finally do factoring algorithm. And yeah, here we just give a little bit of description of what's factoring. And factoring is that you are given a composite number n, and so you want to find two non-trivial factor of it. Okay, so you're given a composite number n, then you know it's something times something. So you want to find two non-trivial factor pq such that p times q equal to n. And we are going to use factoring to do use order finding we just talked about to do factoring. And so basically what we do is that we are going to find the random x and find its order r, okay, by our order finding algorithm. And we see that we are lucky, then this r is an even number, and okay, and then if r is an even number, then we can find kind of a square root of x under n. Okay, so we can find some number. This is annoying. I should swap x and y here. Sorry. So maybe let me write this. Okay. So we want to have some y square. Sorry, here the x and y is reversed, and so for now let's try to talk it here. So we find some random number y, and and we find with using order finding to find its order r, and then we can find the square root of y by, if r is even, by just having y to this r over 2 power. Okay, and then we will see that with very good probability this y to the r over 2 because so x equal to this y to the r over 2, because x squared equal to 1 modern, then x plus minus 1 has a good probability to be a factor of n. Okay, and yeah, so I guess let's go to next slide. It's a little more detail. So the sketch of our factoring algorithm is we choose random x between 2 to n minus 1, and so first we check that it is not a factor of n. It doesn't have a factor of n, so x and n is co-prime to each other. And x and n is co-prime to each other, then you can use order finding to find the order of r, the order r of x, and under n. Okay, and once again, the order finding algorithm is the only part, quantum part. So you need a quantum algorithm to do the order finding. Okay, and then we need to start getting lucky. And so if your r is the odd number, then we are unlucky. Okay, and we claim that with some number theory, you can show that your x was uniformly random, then this r being odd just happen with constant probability. And if r is even, then you can calculate the square, kind of the square root of x, that's x to the r over 2. Okay, and yeah, and here comes a bit of the calculation here. So we know that x r over 2 square equal to 1 modern, because well, this thing square is just x to the r, and we know x to the r equal to 1 modern. That's how the order being used, why the order is defined. Okay, and so we have kind of this x r over 2 square equal to 1, and we can move this 1 to other side and try to factor this thing. Okay, So we see that x to the power 2 minus 1 times x to the power 2 plus 1 will be 0 modern. So this is a multiple of n. Okay. And now, now we have this kind of a sketch of what happened to describe the possibility why this thing has high probability to be why each one of them has high probability to be a factor of n. Okay, so we think n is about some p times q, and then you can think about what n is equal to p times q, also equal to something times something. Okay, and so you can think about, so this is really rough. Really rough, but yeah, hopefully, but hopefully this gives you some idea. So you can think about how p and q is distributed on those two factors. So there are four possibilities. First one is this factor gets both the factor p and the q, and this gets 1. And or this gets both factor of 1 and this gets both p and the q. And or this one can get a factor p and this one can get a factor q, and this one can get some factor q and this one can get some factor p. Okay, and yeah, and then we can analyze the case one by one. And the first case is actually impossible to happen because the first case says that x to the power 2 equal to 1 modern. Okay, and that means power 2 is a period of x. But we already know that R is the smallest number that has x is a period is the smallest number. Okay, so you can cannot have a smaller number than R such that x to this number equal to 1 modern, because we already say R is the smallest number such that x to R equal to 1. And yeah, and so this case is really impossible because it violates the definition of R being a period of x. Okay, and then the second one is says that so we have this thing is equal to 0 modern, and so x to the power 2 plus 1 equal to minus 1 modern, and this thing we just being unlucky. Okay, and then the next case, then the next two cases we are lucky because we know. The next two cases we have this thing having either this thing being equal to p modern, or or this thing equal to q modern. Okay, so okay, and so in this case, then we see that this thing is basically p, and or this thing equal to q, doesn't really matter. And so if this thing is a p modern, then you just have you just need to find the greatest common divisor between this x to the power 2 minus 1 and n, and you will find either p or q. Okay, and yeah, so that's the idea of our factoring algorithm. So yeah, and so we try to find so we draw a random x and we find the order, and then once we find the even order, we can have this square root of x, and then we try to find a factor between square root of x and n. Okay. And if we are lucky, then we have a non-trivial factor. Okay. And then finally, we have a small part of we need to find. So those are two possibly really big numbers. So those two numbers can be both order n, and we need to find their greatest common divisor very fast, very efficiently. And fortunately, there was an algorithm that was known to do this very efficiently, and that's this Euclidean algorithm. So we just keep dividing those two numbers by each other, and yeah, so this should be terminated in order L operation. Okay. And yeah, so we have 2 more minutes, so I presume we can stop here, and let's start a 10-minute break. Let you look at this, and yeah, then we will go into detailed description of factoring next class. Next class after the break. Okay, yeah, so let's have a 10-minute break. 有什么问题吗？
专题就是我图文习惯，然后他说专题那个同意书可以线上填，然后可以用 email 当证明，
好，
叫做
好啊。
所以问说可不可以用之前就是我寄信对，然后你回复的那个当证明。
寄信的，那应该就那看西班同不同意啊？西班同意，
那他说可以啊。
那可以，那就可以。
然后我在想题目，
这样。
如果是前天讲那个有几个基本的 gate，然后去凑其他的 gate 的那个题目啊。
可以啊，都可以当题目。
想说如果只是做延伸法，好像有人做不了。
凑 gate 不知道，可以凑凑看，我也不太清楚怎么凑，就是。
有 SYD， 然后有 IS。
对啊，可以凑凑看。凑 gate 就可以凑凑看吧。说不定会用一些蛮深的点，我在想的话。有少看到这个，就可以算算看，可能自公系可以用一些计算的方法去凑凑看，不知道结果会怎样就是。 Okay, I think we can get started. And oh, sorry. Yeah, I think we can go back and get started. So, any questions so far? And yeah, so let's go to factoring. And once again, the idea of factoring is we find this random number x, and then we are lucky enough, then we can get we find this random number x, and we use the quantum order finding algorithm to find this order r. And then if we are lucky, then from r and x we can find the factor of n. Okay. So first we need to get lucky such that r is odd. Sorry, r is even. So you can compute x to the r over 2. And if you are also lucky, then x to the r over 2 is now equal to -1 model. Then you can just compute the greatest common divisor between x to the r over 2 minus 1. And okay, and yeah, and if there is no question, yeah, and if there is no question, yeah, then let's go see the rest of the slide. And the first is a small review of Euclidean algorithm. So how do we find the greatest common divisor of two numbers efficiently? It's by just doing division between then one by one. Okay. So I guess in Chinese we call this 整准相除法. And yeah, so for example, we have this 210 and 45, and we want to find its greatest common divisor. Then we have 210 divided by 45, and it's 4 with remainder 30. And then you divide 45 by 30 now, so you have 45 divided by 30 equal to 1 with remainder 15. And finally, you divide 13 by 15, you see first 13 divided by 15 is 2 with no remainder. Then you see that once we get no remainder, the last number here is the greatest common divisor between those two numbers. So greatest common divisor between 210 and 45 is 15. Okay. And and then I think the last thing we need to say is that we need to claim that our being lucky part actually happened with good probability. And here is a theorem that we basically copy from the textbook. It says that if n is so we need excuse me, we need some more condition here. So if n is can be written as this way, so some first prime to the p1 to the alpha 1 times p2 some pm to the alpha n, where each of those p1, p2 to pm is a prime. And then we need to have a bit more conditions. So first is that n need to be odd, so all those p not equal to 2, and also m need to be greater or equal to 2, so we need to have at least two different primes here. And if you have those two things, then the probability that we are lucky will be pretty good. The probability we are lucky, so we are lucky is when r is even, and x to the r over 2 equal excuse me, this is when I is even and x to the r over 2 not equal to -1. Okay, yeah, so that's the two conditions. So we need to have r even and x to the I over 2 not equal to -1. Okay, if that happen, then and that happen, then we can find the factor of n from x and r. And we see that this happen with very good probability is 1 minus 1 over 2 to n. And so if we have n at least 2 here, then it's at least 3 over 4 probability. Okay, and yeah, so that's a very good constant probability because you can keep trying for different x. Okay. And yeah, and we have this happen when x is uniform random from 1 to n minus 1, and it's co-prime to n, and I is I is once again a period which is the minimal integer r equal to 1 model. Okay, yeah, so we just with this one theorem to here to say that with very good probability our x randomly drawn x will be good. Okay, and yeah, so finally now is our procedure for factoring with all the detail. And so basically we need to check everything in this theorem here matrix. And so first we need to make sure n is odd, so we check whether 2 is a factor of n. We check whether n divides n. And so this notation here means that 2 divides n. Okay, and so if 2 divides n, then obviously you can factor n by just saying 2 is a factor. Okay, and then also need to check that n is not so this m is greater or equal to 2. So we need to check that there is at least one different prime. Okay, here, and basically we need to check n is not some prime to some power. Okay, because we already know n is not a prime. Okay, and to check that n is not some prime to some prime to some non-power, and we basically just taking roots of n. Okay, so we try to compute a square root of n, cubic root of n, all the way to Lth root of n. Okay, because n is at most L bits, and so the largest possible alpha here is L, because n is less than 2 to L, and so it's less than, okay, because we know n is L bits. So excuse me, let me find the bit here. Yeah, so we only need to check this to we only need to check this to Lth root, because we know n is less than or equal to 2 to L, and yeah, and so it's less than or equal to p to L for any p, for any prime. And yeah, so we need to check this from 2 to L, and so there are L things to check, and you can show that each of those taking roots can be done in order L square calculation. So totally checking those things can be done in order L cube calculation. Yeah. And well, if you check yeah, and you check all those, and if n actually equal to some prime power, then just output the prime. So or maybe it's not even prime. Yeah. Yeah. I guess if you are really lucky, then A is not even prime. But anyway, if n equal to power of something, then you can just output is A here. Okay, and yeah, and so after these two steps, we have checked that our n satisfy both of those conditions. So n is odd, and n has at least 2 different prime factor. And now we start picking our x. So we can draw x from, so we were saying x from 1 to n minus 1, but obviously 1 will be not good, so let's have x from 2 to n minus 1. Yeah. So let's draw x from 2 to n minus 1, and then we check that whether x and n are co-prime to each other. Okay, And well, if x and n are not coprime to each other, then we are very lucky. We already find the factor of x and n, and so this greatest common divisor between x over n will be just a factor of n, non-trivial factor of n. Okay, and yeah, so if you are not coprime, you already find the factor. Okay, and then up to this point, we have checked everything. So on the first step, we check that n is odd. And on the second step, we check n has more than one prime factor, and here we found this uniformly random x that's coprime to n. And then finally, we can use our quantum order finding to find the order R of x with respect to n. Okay, so now we use the quantum part to find this order R. Okay. And as we said, then we want R to be even and x to the R over 2 not equal to 1 mod n. Okay? And so I guess I should write mod n here. Not equal to the 1 mod n. Okay? And if we are getting a good R, then and then as we said before, or as this theorem claim, well, I guess we didn't have a theorem, but as we claim here, this we just compute the GCD between x to the R over 2 minus 1 and n. This will be a factor of n. Okay, and so this thing happen by this theorem happen with probability at least 2 to the over 2 to n, and n is at least 2, so this is greater or equal to 3 over 4. Okay, and this happened with 3 over probability, and if it didn't happen, then we just go back to pick a different x, and with not too many rounds, you can find a good x and r, and then you will find the factor of n. Okay, so this should terminate in constant number of rounds. Okay, any questions so far? If not, then let us see a bit of an example. So continue from previous example. So previous example, we say that when we have n equal to 15 and x equal to 7, we have that the order of x equal to 4. Right? That's this one. Oh, sorry. So we are 28, then maybe 20. No. 19. Okay. Yeah. So in this example, with n equal to 15 and x equal to 7, we do by just basically brute force calculation. We see the order of 7 is 4. Okay. And we say order finding can find this order 4 pretty efficiently. Okay. And then back to here. Okay. And with r equal to 4, then let's see our mathematical analysis check out. Okay. So r equal to 4, and so this r is even, and then we can check the square root of x. Square root of 1 here. Okay. Sorry, I keep saying square root of x. So, but we actually getting kind of a square root of 1. So we want to get a non-trivial square root of 1 from here. Okay. And but anyway, x to the r equal to sorry, a typo here. And we want x to the r over 2 equal to so 7 to the 7 square. Okay. 7 to the 4 divided by 2 equal to 7 square, and 7 square minus 15 is 9 equal to minus 1 equal to actually 4. 7 square equal to 49. Okay, so this is 49 here, and 49 minus 15 will be equal to 4. And and anyway, so this is minus 1, and we know the algorithm should work, and then we can do what do we say? So we compute the GCD between x to the r over 2 minus 1 and n, and that can be the GCD between 48 over 15, or you can just say it's from the calculation here, it's also 3 and 15. Okay. And anyway, you calculate the greatest common divisor, you see it's 3. And then yeah, we see this works because 3 is a factor of 15, and that's because 15 equals to 3 multiplied by 5. Okay? Yeah, so that's our detailed description of factoring algorithm. We need to check a whole bunch of detail. But in the end, we find, we pick a random x, find the order r, then we compute the x to the r over 2, and have the GCD between x over r over 2 minus 1, and then. Okay. And if there is no question, then let's go to the last part of this chapter. Okay. And this, I guess, so we have been talking about factoring algorithm in terms of this phase estimation. Okay. And yeah, we were saying that we have the, I guess let's come back. So really back, like 5. Yeah, we were saying that we were doing phase estimation on this ux, and then we said the eigenvalue of this ux is related to the order. Okay. But I guess historically, when Peter Shor comes up with, okay, so we go back to order finding. Okay. And so this order finding algorithm, and I guess it was actually I would say that it's motivated by Simon's algorithm, and because we can do quantum Fourier transform really fast. Okay. And so I guess this is really order finding algorithm in another view. Okay. And and so here we are going to talk about order finding algorithm is in another way to do analyze and to see how they are related to Simon's algorithm and quantum Fourier and Fourier transform. Okay, and so yeah, the order finding algorithm we have here, and as we said, this is the phase estimation of this u to the k, u sub x to the k, and and we have the secondary register start with 1. Okay, and so at the start of the algorithm, we will put the first register as a uniform superposition with of everything. So k from 0 to bigger minus 1. Where here for simplicity we say bigger equal to the t minus 1. We don't have the extra. We don't take the extra. Excuse me. Yeah, for simplicity we don't take extra error number here. Okay, and yeah, and with if n is not to the power minus 1, then you can create different superposition here. But here, anyway, here you want to summation from 0 to bigger minus 1, and I guess it doesn't really matter. But anyway, yeah, for simplicity, let's assume bigger n equal to the t minus 1. Doesn't really matter here. Okay, and then yeah, and then as we said, then we have this control on first register apply u to the k, and so what happens on second register is second register become x to the k model. Okay, and so you are equal superposition of k from 0 to n minus 1, and k on first register, x to the k on second register. Okay, and then we go to the yeah, and yeah, before then we say we just express the second register as eigenvectors of this u to the k and do analysis later. But we can do another way to do analysis is we use the principle of implicit measurement, because as we see, we just have the output from the first register, right? And so we only care about the output from first register, and we don't do anything on second register anymore. And so we can assume that we measure the second register. Okay. So we assume we measure second register and see what happened on the first register. Okay, and we measure second register, and so the state just before this measurement, because measurement on second register was this k tensor x to the k, and as we know before, as you know, those things should be the thing here should be 1x squared. Sorry, it should be 1 x to the cube. Sorry, x squared x to the cube all the way to x to the r minus 1 and x to the r equal to 1. Okay, so you know the second register is actually a cycle between all the possible power of x here. Okay, so it's either 1 x to the 2 x 3 all the way to x to the r minus 1. Okay, this was what happened in our example. Sorry, 19 here. Okay, yeah, so you see first register was 1 2 0 1 2 3 all the way to the t minus 1, and second register was 1 7 4 13 and then 1 7 4 13 etc. It's keep repeating itself. Okay, and yeah, and in that case, then when you measure the second register, we'll pick out one of the possible value of this power of x. Okay, and let's say it's some number k. Okay, yeah, sorry, it's something. Okay, it's something. Say you measure and you get x to the some power here. So say you get x to the k here. Okay, for some k. And what happened here, so very similar to Simon's algorithm, is that we'll project the first register back to everything that has x to the k on second register. So as k and k plus r and k plus 2r all the way to k plus n minus r. Okay, and if you write that in complex notation, that's k plus some lr. Summation of L from n minus r n over r minus 1. L from 0 to n minus n over r minus 1. Okay. And so as we said, this is similar to Simon's algorithm. Simon's algorithm, we say that after you apply the unitary, you have x and f of x here, and you measure this f of x, then you project all the x to the x that give you the same f of x. And during Simon's algorithm, there was only 2x. There was the function was a 2 to 1 function, and here this is actually a many to 1 function. It's a periodic function. Right, this u to the k is a periodic function with period r. Okay, and with every r here, with r here, with every r application of u, we'll go back to the same thing. Okay. And yeah, so we will get this periodic input x here. So you see that every one of them has a distance between having r here. Okay, have a k and a k plus r and a k plus 2r. So you see increasing the number here by r each time. Okay, plus yeah, plus minus r. And here. Here we have a very complex form because so we assume we have this nice property such that r divided by n here. Okay, so we assume r divided by n, so we can this is exactly we have exact number here. Okay, so we don't have a weird length of tail here. Okay, so such that this summation is the same for every k. And you are summing the number of term for every k. Okay, and yeah, so we assume r divides n, so we have a next expression here, and well, k will be uniformly random. So k will be uniformly random from 0, 1, 2 to r minus 1. So for simplicity here, we assume this thing here. And I said this is similar to Simon's algorithm, where you measure a second register, although your output doesn't care about second register. But that will force your first register into a simpler form, so you can do analyze later. Analyze it later easily. Okay, so assume we have this form, and that was our old writing of first register into something. Okay, and then after that, we apply inverse Fourier transform on the first register. Okay, I guess I should put a blank page here. Okay, and let's do this way. Okay, and now we have this sequential thing, this evenly spaced sequence, and then we see that when we do quantum Fourier transform on this thing, then we'll get our nice S over R. And so you apply inverse Fourier transform on this thing, and so it was this summation L and K plus LR, and you do inverse Fourier transform, then you just get another summation J, so J from 0 to n-1, and then this K plus LR become some term in this exponential factor. So inverse Fourier transform, you have e to the minus 2 pi jk over n. Okay, so, and the k was actually this k plus k plus LR. Okay, and you have this summation J. Okay, and now we try to express this thing in a nicer form. And as usual, we switch to the order of summation. So instead of sum L, sum J, you have sum J, and you take out everything depending on J. It's minus 2 pi jk over n, and then you have everything summation L. So summation L and e to the 2 pi and JLR over n. Okay, JLR over n, and we write it in a nicer form. We write it as JL over n over R, because we see we are actually we see that we are actually summing over n over R terms. Okay, there are actually n over R terms for n over R different L, because there was a big n there was a big n terms here and big n terms, but we only pick out every R terms, so there are n over R different terms here. Okay. So so we are summing over n over R different terms here, and this number here, we see that is a very nice form. Okay, so it's sum over summation over those exponentials. So this equal 2 pi I J over J over n over R. Okay, so if you say this is n prime, if you just say n over R is some integer n prime, then it is summation L from 0 to n prime minus 1, e to the minus 2 pi J over, oh sorry, I forgot the prime here, J over n prime. Okay, and this summation we have seen before. This is once again the Fourier analysis summation. Okay, n prime here. Okay, and once again, this is this Fourier analysis summation. This is e to the 2 pi jk over n equals 0 for every k not equal to 0. And so n is really n prime here, and I guess instead of sum j, we have sum L, and k is actually equal to j here. Okay, so when j not equal to 0 here, this summation will sum equal to 0, because you are summing over those equally spaced out points on the unit circle. And when j equal to 0, then you are just summing all points once here, and the summation should just equal to n prime. Okay, and so you see this thing is equal to 0 when j not equal to 0, so you actually only get j equal to 0 term here. Sorry, j equal to 0 mod n here. Okay, if j is not equal to 0 mod n, then this is 0. If j is equal to 0 mod n, then this is n prime. Okay, and and I should have said s before. Okay, and k to s, then we see that at the end, when we measure this in computational basis, you only get j such that, oh sorry, I guess that's different. Sorry. Oh, never mind. Yeah, so k is different from s. Sorry. And so we have this thing, and because n prime equal to n divided by r, So J just equal to S over R times N. Okay. And yeah, that's the same as our analysis before. So J will be S over R times N equal big N equal to 2 to the T. Okay. And then we see that everything is drawn with equal probability. So the amplitude of every J is actually the same. So amplitude of every J is this N prime times this square root R over N. And we have a factor e to the minus 2 pi I J over N times K, but it doesn't matter because it's a phase. And when you do computational basis measurement, the phase you don't see. Okay, and yeah, so the amplitude will be this 1 over square root R, and you see every S is drawn with probability 1 over R. And yeah, let's check out because there should be R different S here. Okay, and yeah, so once again, you get this J, and you normalize it by divide R, and just as before, you get random S over R. Okay. And then here we have a very clean calculation because we assume that R divided by N. Okay, so back to here we assume R divided by N, and if R doesn't divide by N, then as you see, this series will get cut off at some point, and actually every K has a different a bit of a different probability, and the analysis will get dirtier, but that's basically the same analysis of the phase estimation accuracy analysis, and yeah, we skip that, but if you want to look into detail, you can look into Nielsen and Trump. Okay, and I guess that's the last slide here, but I want to talk a little more here. Okay, is there something I can? I guess not, but yeah, and so I guess here we talk about how this thing is related to Simon's problem, and but then I want to talk a little about how this works, how is this related to Fourier transform. Okay, so idea of this related to Fourier transform is we have this kind of input vector, and we apply Fourier transform it, right? So we have a vector that's this. We have this vector that's basically K plus K plus R plus K plus 2R plus dot dot dot, right? So we have this input evenly spaced signal inside, okay? And so this kind of a signal, so if you think of this vector, then it will look like this, right? So it will look like something on K and something on K plus R, something on K plus 2R. So we're trying to draw this vector in like a 2D plot. So yeah, so it has amplitude on K plus R, amplitude on K plus 2R, etc. And this thing is actually famous signal. So if you think about this as a kind of like a function, function of what's the amplitude of the computational basis x, and so this kind of signal is called the impulse train, and it's famous because we know that if you do Fourier transform it, you will get another impulse train. Okay, so if you do Fourier transform on impulse train, then you can get another impulse train. Okay, and okay, so Fourier transform impulse train, you will get another impulse train. And what's funny here is that the spacing here are related, and so basically here the space between the impulses is R, and you can show that. Then you do Fourier transform, then the space between the Fourier transform signal, you have the space here will be 1 over R. Okay, and yeah, and so that's how we get our our S over R, right? So we get our S over R because we get a uniformly random S here. Okay. Because now the spacing is 1 over R, and you get a random S, then you get this S over R. And also interesting thing here is, the annoying thing about here is you have a random K, right? Random K here. You have a random K here, and so you don't really know, you don't know, you get a random K, so you have a random shift on the starting position of your impulse train. But what's nice here is you apply the Fourier transform, and then this random K don't actually affect the starting position of your Fourier transform, this impulse train here. Okay, so this because for every K, we actually see that this S over R train always start with 0 here. See, it's always 0 over R, and 1 over R, and 2 over R, etc. And then you may ask then where, so Fourier transform actually preserve the information about the input, because you can always apply inverse Fourier transform back. And so you may ask, so where does the K information go when you apply this Fourier transform? And that's a part we kind of gloss over. This phase that we say is irrelevant. Okay, and so the K information actually don't affect the distribution J here. So you see that for every K, you get the same impulse train. The impulse train plays at the same J here, and the K just become a phase on all the impulse. So you have each impulse is on phase depend on K. But when we do computational basis measurement, we don't see a phase on K, and yeah, so we can just sample from this impulse train with spacing 1 over R. And so basically we say we sample enough things that place it on S over R, then we can estimate what this R is, and then we know this R is, then we know this R. Okay, and yeah, so that's why people see that when you can do quantum Fourier transform, then you can solve this order finding problem, because you see that you have this very ordered state, and this very periodic state. You have this very periodic state. Then you as input, then you do a quantum Fourier transform it. Then you get another periodic state, and the periodic state will tell you the period of your original state. Okay, and yeah, I think that's all I have today. And so if there is no question, we'll stop early once again here, and see you on next Tuesday. And I think we'll probably starting on Grover's algorithm. Okay, yeah, so see you on next Tuesday. Okay.